Our next name of our next speaker is Volodymyr Mykhaylyuk, and Mikhailuk, I'm sorry. The title of the talk is Extending of Partial Metrics.
Well, uh, first of all, I thanks the organizer of the conference for the opportunity to participate and make my report. And my report concerns notion of partial metric and named by extending of partial metric. We start from notion of partial metric space and partial metric. This is the definition of partial metric. The function p is called the partial metric on X if this function satisfies the following four conditions. This conditions is closely connected, this corresponding condition of metric space, and if we have that p of xx is equal to 0, we obtain axioms of metrics. This notion was introduced by Matthews in 1992 and used in fixed point theory intensively and in computer science. But topological properties of partial metrics is not investigated closely and wide. The classical example of partial metric that is not metric is maximum of 2 points in zero plus infinity, but it is easy to see that the condition that p is only greater than 0 is not very essential, because we can consider such function and this notion name it not partial metric, but many properties of such function is analogical to properties of partial metric space and partial metric. Well, it is not difficult to verify that this function satisfies corresponding conditions. Topological properties of partial metric space is closely connected with another generalization of metric, namely quasi-metric. Recall that function q is called quasi-metric is if it satisfies the following two conditions, and if we have only condition q2, this function named by quasi-pseudometric. And for partial metric p, it is easy to see that the function p of x y minus pxx is a quasi-metric, and this quasi-metric generates corresponding topology, and this topology named by topology of partial metric space. In particular, such balls generates a base of topology of partial metric space at the point x. And the corresponding function just a moment, which is the sum of this quasi-metric and conjugate quasi-metric is corresponding metric on partial metric space. that is closely connected to these properties of partial metric tool. The classical example of quasi-metric space that is not partial metric is classical counterexample Sorgenfrey line. Namely, if we consider such function generates corresponding topology of Sorgenfrey line. Such function is quasi-metric, and if epsilon is later than 1, we have the corresponding ball is corresponding semi-open interval from x to x plus epsilon. And this quasi-metric space has any partial metric such that this partial metric generates this topology because any partial metric space has G delta dense if it bare space then it has G delta dense subspace which is metrizable, and Zorgis-Frey line has not such subspace. Therefore, this space is not partial metric space, partial metrizable space. Well, since partial metric is closely connected with this metric space and with quasi-metric space, naturally, the following question naturally arises: which theorem from theory of metric space can be generalized by the case of partial metric? In particular, we consider now a problem on extension. The following well-known theorem was proved by Felix Hausdorff in 1930. If we have a metrizable space and closed subset of this space and compatible metric, we say that metric is compatible if corresponding topology generated by dA coincides with topology A as a subspace of X. Then there exists a compatible metric D, which is extension of dA, of dA. And the following question naturally arises: can we prove analogical theorem for partial metric? Namely, if we have a closed subset and some partial metric on A compatible, does there exist a compatible partial metric P on X such that the restriction to A square is equal to PA? Well, for investigation property of partial metric, the function P of x play an important role. In particular, for this problem of extension of partial metric, we need following two propositions. It have not difficult proofs. The first proposition says that if we have a partial metric space, partial metric on X, and the diagonal function P of x is one Lipschitz function with respect to corresponding metric GP. Recall that this metric is equal to the sum of dq and dq minus 1 conjugate. It follows immediately from this not difficult inequality. Well, and inverse property says that if we have function f, which is one Lipschitz with respect some function d, then we construct such partial metric that this partial metric has function f as a diagonal function and metric g as a corresponding metric dp. This means that we need um, extend only corresponding quasi-metric uh, in the problem of extending of partial metric, namely um, we can solve a corresponding problem in such a way. Let PA is be a partial metric, QA corresponding quasi-metric, and GA corresponding metric, and FA corresponding diagonal function corresponding to PA. And assume that there exists compatible extension of quasi-metric QA, extension Q. Then we can construct the metric G in such a way, and this metric G is an extension of GA. Then, using theorem of McShane, we according to corresponding proposition, FA is one Lipschitz function with respect to D. Then, according to this theorem, we can extend this function to the some function f on x. Then we consider function p, which is a compatible extension of PA. Notice that this condition is a necessary condition for extending of partial metric because we need the compatible partial metric extension, and this means that corresponding quasi-metric is compatible too. Well, because topology of partial metric generates by corresponding quasi-metric. And this means that we need investigate only this question: the existence of compatible extension of corresponding quasi-metric. And clearly that this problem is a problem closely connected with this Hausdorff theorem, and we can use classical method of proof of Hausdorff theorem, namely Bing's method. Namely, using this method, we can write in such a way. Namely, we obtain the following proposition, that we have quasi-pseudometric space and closed subset and compatible quasi-pseudometric on A. Then there exists such that this compatible quasi-pseudometric is less or equal to the primitive quasi-pseudometric Q. Then there exists a compatible quasi-pseudometric tilde P on X such that this extension is less than equal to Q2. The construction of this extension we can write in such formula, and this means that the problem of extension we can reduce to the existence to the existence of such quasi-pseudometric Q such that P is less or equal of Q. Well, we can solve this problem in the case of bounded quasimetric P. Namely, uh, let XQ be a quasi-pseudometric space and A be a closed subset and be a compatible bounded quasi-pseudometric on A. This condition bounded by C. Then there exists a compatible quasi-pseudometric R on X such that we have such inequality, needed inequality for our quasi-pseudometric P. The construction of such quasi-pseudometric tilde P we can make using two steps. The first step is extension of P. The first step is the extension of P tilde P in such a way. And the second step, I is equal to tilde P plus Q. Then such quasi-pseudometric generates the same topology as Q and such that P is less or equal to R because tilde P is an extension of P. Well, the following counterexample shows that the condition of boundedness of P is essential, namely, there exists a quasi-pseudometric Q on a countable set X such that and some quasi-pseudometric P on A, which is compatible with Q on A, and such that P have not any extension such that the topology of TR is weaker than the corresponding topology of TQ. And the construction of this example is the following. Let the X consist of countable elements, and all xn are isolated in this space if you consider such quasi-pseudometric, and x0 is a closed one-point set such that any neighborhood of any xn x0 belongs to any neighborhood of any xn, but x0 is the isolated point. And in this situation on A, on the discrete subset, we can consider P as P of xn is equal modulo of n minus m, for example. For example, this function is not bounded, and it's not difficult to verify that this function has any needed extension. Well, and the main result, positive result, is the following. Let X be a partial metric space and be a closed subset, and PA be a compatible partial metric on A. Such that corresponding quasi-metric is bounded, then there exists a compatible partial metric P on A such that it is extension of PA. Well, and uh, the references, which consist my report. And that's all. Thank you very much
Thank
for
you.
our attention.
Thank you for the talk.